So as you get going with slightly more complicated codes beyond working with, let's say, number of thread blocks, number of threads within a block, etc., you'll get into issues, and not always it's clear how you are going to identify what those issues are. And therefore, I thought I have created these slides to see if we can get some benefit out of what needs to be done when you get into these issues. There are some good practices which you can follow. There are other ways. I mean, you can always add printf and see if you are getting output, but that works primarily in the sequential setting. In the parallel setting, sometimes there are issues. And that's what we would like to understand here. So that is one part, that is the debugging part. The second part is profiling. As you notice, there is a small bonus mark in this assignment too, if your time is less than half of the average across all students. So that is added because finally the parallelism is for efficiency. And we would like to give some benefit to students who put in an effort to make their course efficient. Slowly as we go along, you'll realize that this performance is actually quite paramount, and it's possible that you might lose performance just by not doing certain things, right? So for example, we have been talking about thread divergence, memory coalescing, bank conflicts, etc. And as we move to synchronization and more complicated stuff, you'll realize that it's very easy to lose performance just by ignoring certain facts. Thankfully, these optimizations for performance can be done incrementally, and we would like to keep an eye on these as we go along. So the next part of this set of lectures, which are called as support, will be dealing with profiling. How do you profile your codes, and how do you identify where the bottlenecks are, and so on. So I'll take one small examples in each of these cases and mention to you how that needs to be done for both debugging and profiling. Right. So let's delve into this. So in general, debugging parallel programs is difficult, right? Even writing parallel programs is difficult because you need to worry about, now you need to think, let's say, in parallel in some sense, right? Not every program is nicely parallel a of I equal to I, right? So therefore it becomes a little problematic whenever there is some sort of synchronization required across threads. So writing parallel programs is difficult. Debugging it is further difficult because you think that everything looks good. And we have this notion of sequential thinking all along in our mind because our brain works sequentially. Right? At least we have one brain, let's put it that way. We don't have multiple brains like Ravana. Non-determinism is one of the aspects that comes into play. So can somebody tell me what non-determinism means?
I think it means that even if we keep all the controllable parameters in our control, the output may not be exactly the same every time.
Correct. So it's possible that everything, whatever you write in the program, right, that is what is the one that is guiding the output usually, right, at least in sequential programs. And whatever we write, okay, I run it once, the sequential program on CPU, I get one output. I write it again, I run it again, I get the same output. I run it again, I get the same output. That is what is the expectation out of usual sequential programs, and that is called as a deterministic program. It's a deterministic output. Contrast it with something even in the sequential setting where I'm generating some random numbers, right? And that random number seed is changing across program runs. If that happens, then your sequential program might give different outputs, right? So there is non-determinism in the output. At the very, very fine-grained technical thing, you can always say that, okay, that also is deterministic once you get into how random numbers are generated. But from the perspective of a user, we can always say that, okay, I don't know what the output of this program is going to be because the seed might be changing based on time and so on. More so happens in the parallel setting where now I'm talking about the programs. For example, we wrote s equal to 0 and then s plus equal to 1, s plus equal to 2. That program did not have any sync threads. And then the output was s equal to 3 sometimes, s equal to 1 sometimes. This is non-determinism. Right? So the output is changing across program runs without you making any changes to the program. There was no randomness in the program, but the output was changing. now the output as a printf is just one part, but the behavior of the program might also change. For example, you might be writing to certain memory locations, you might be writing to some socket which is going into some network, or you are writing to a file. All of these external effects will go on changing if you run the program multiple times, and that is a little surprising. It can also be unacceptable in many cases. And determinism is easy because you can always argue about correctness whenever there is determinism, right? This is the input, this is the program, this is the output, right? So if you have such a triplet all the time satisfied, then you can argue about the correctness of the program. Not only correctness, but not correctness always, because this I am talking more on the test case based, which is not never complete. But at least you can say that this seems to be a reasonable thing to do. When the output is changing, it becomes a little difficult, right? So if you ask what is your age, sometimes you say 18, sometimes you say 20, and that's definitely not acceptable. That is one part. And sometimes it so happens that if you want to, if somehow the output that you get is deterministic, even in the parallel program, the intermediate values might differ because of the parallelism. So think about it this way, that you have, let's say, s equal to 0, and then there are different threads who are doing s plus equal to something, let's say s plus equal to id, right? At the end of the output, assuming that this s plus equal to id is done without any interleaving, that means it is done atomically, then the output that you get is always going to be deterministically accurate. You will always get the same output. But the intermediate values that S will have will go on changing depending upon how threads are scheduled by the scheduler. And where is the scheduler? The scheduler is in hardware. Do you know how the scheduling is done? No. In fact, you need not even know. In this case, you are going to get different outputs at the intermediate levels, the different values at the intermediate level, but the output is going to be the same. So if you want to debug the program, you might get possibly the same output, but intermediate somewhere you are probably expecting something to happen in a particular manner, but it's not happening the way you want. And that can also add complications to your life, I mean, debugging life, I would say. So therefore, the debugging becomes quite a bit of challenge in the context of parallel programs, not only on GPU, but on CPU, just that the issue gets kind of increased or exacerbated on the GPU because we are talking about a large number of threads. In case of CPU, for example, you might, I mean, sometime if the number of threads is small, let's say 8 or 4, you can at least think about, okay, this thread is doing this, then this thread. You can manually pinpoint this thread is doing this exactly at this point, and therefore these are the possible interleaving, let's say 2 to the power 4 or 2 to the power 8 number of interleavings possible across all of these threads, which is still manageable at every step. I mean, if at all, it's so crucial. But on GPUs, when you have a very large number of threads, 2 to the power, let's say 1000 or 2 to the power 100 of 1000, that seems a little problematic to handle manually. So there is a tool called GDB on to debug to debug sequential programs on CPU. Similarly, there is an extension for CUDA, which is the cuda-gdb, which is for debugging CUDA programs on real hardware, not on the simulator. There is a GPU simulator also, but this is for the real hardware. It has extensions to GDB, which means that most of the commands of GDB are going to work, but then there will be commands to figure out what is a, let's say how many threads are running, and how many thread blocks are there, what is the value of a particular thread. I mean, you need to go to a particular thread and identify the values of its local variables, etc. So all of this is possible. Thankfully, it allows most of what is handled by the GDB, which means that you can add a breakpoint. You can single step through the program, and you would wonder what is single stepping when you are talking about parallel execution. Yeah, there will be issues because of debugging. So for example, I don't know if some of you have noticed, but if you run the sequential program, let's say you have a C file, compile it, run a.out, you find that there is a bug. right? I mean, there is some problem, some issue that occurs. But when you run it via GDB, suddenly that issue doesn't occur, right? And that can become problem, right? So has anybody faced this issue, and what could be the reason behind such a behavior? Any suggestions? So the issue is that you run a.out, you get some problematic output, right? Some erroneous output or some error, runtime error, let's say. But when you run it via GDB, you don't see that output. You don't see that problem. Any suggestions why that might be happening?
Sir,
Yeah, because
I have seen that happen, and maybe it's because when we run it through GDB, the GDB allocates a different set of environment variables apart from the existing environment variables that would be present, and a different address space to the whole program. Maybe that's the reason.
okay, that's a good analysis. That's possible. So there are, since it needs to check some of the let's say environment of a.out, it might add some headers to each of these environment variables, right? And that can change the behavior of the program, right? Earlier there was a problem outside the address space, but maybe the address space is turning out to be now within the process's address space. That is one. Another thing that can happen is the timing issue. As soon as you are single stepping, you are changing the time at which it is occurring. Whereas if there is a time-based error, then via GDB you might not be able to find it unless you actually let it run arbitrarily via GDB. Okay, so these issues can occur, and similar issues can occur even in the context of parallelism, and that can be really difficult to resolve. As well as it supports reading writing of memory contents, which means that you can find out what is the value of a variable at a particular place. Let's say you have put a breakpoint and then there is a value that you want to read, as well as you can modify the memory location, right? So this is something which the debuggers usually support, that okay, I have debugged through this part, or I have stepped through this part. At this stage, the value should have been 0, but the value is 1 for this variable. Let me set it to 0 and see if it works fine, right? So this allows you to modify those contents at runtime while the program is running, and that actually changes the memory location, and then the program can run through further. So these are very powerful debuggers which have been created, which you can utilize for your purposes. So let's take a very simple example here. I have an int star x, a pointer, which I'm passing to the kernel and then doing nothing inside the CPU. On the GPU, I'm just assigning star x to 0, assuming that x has already been allocated memory, which is not in this case, and therefore I'm going to get some issue. As far as this part is concerned, that itself could be an issue, in the sense that x might be pointing to some memory location, which if it turns out to be null, you are probably lucky. But if it is pointing to some arbitrary memory location, then this becomes more like an, let's say, very similar to a dangling pointer, right? So it is pointing to some arbitrary memory location on the CPU. On the CPU, it might not be a valid memory location, but on the GPU, it might be a valid memory location, in which case star x equal to 0 might just succeed. This is a problem, and thankfully, if you are lucky, you will get an error, a runtime error, right? So just to make story a little interesting, because how will you see that there is an output, there is something wrong happening? In general, when you run this program, you will not see any problem, right? So let me add a printf. And what I'm printing is essentially this star x value, where I expect that it just prints 0 followed by a new line. Unfortunately, it doesn't print anything, and that is my first indication that there is some issue with this code. So prima facie, it doesn't look like any problem to me. Let's say I'm a novice programmer and I don't know that I should have allocated memory, or maybe I miss it. What are the ways in which I should follow that there is probably some error which has gotten executed on the GPU? Now, this error occurred on the GPU. The CPU might not even be aware of it, right? Because these two are totally separate devices. On the CPU, whenever there is a sec fault or something, it's a null pointer exception, etc., the CPU is able to catch that because it's the same hardware which is executing this. Whereas the GPU, it's a very separate memory, it's a separate processor, and therefore the CPU might not capture everything that is happening on the GPU. Therefore, I need some way to identify whether there was an error which occurred when a kernel executed on the GPU or when a function executed which involved GPU. So some of those functions which as a good programming practice we should have are essentially very similar to what happens on the CPU, get last error, right, that we have on the CPU. Here I am going to use CUDA get last error. That error code is of type CUDA error T, and using that error code I will be able to find out the name of that error as well as some error message that is associated with that, which is supported in the CUDA headers. And that can give me that there is some output. So for example, the error number is, let's say, 77, which is this ERR, unsigned integer. And then CUDA error illegal address is the name of that particular error. And the string associated with it is the illegal memory access was encountered. If I had added this, then it becomes easier for me to debug this program because I know that such an error occurred, so I can look up and make sure that things are sane. So I mean, debugging is in general an art, but there are some scientific things involved. For example, whenever there is an error, try to reduce the amount of or the scope of your error, which means that earlier the whole program might be erroneous. Now I know that only the kernel is probably going to be erroneous, where there is, okay, star x equal to 0 is where it has occurred, and so on. Once you have identified once you have reduced the scope and focused on certain lines, after that you can analyze why this has occurred, and from there you can come back here and do a CUDA malloc and so on. Any questions so far on this simple program? Okay, so like this error number 77, there are large number of such error codes which are specified in CUDA, and essentially 0 means, following the C semantics of 0 means there are no errors. There are large number of different errors that you can get. You might not even encounter some of these ever, but just as a curiosity exercise, if you want to try invoking each of these errors, that even the first 10 errors, for example, it might be worth trying just to see where all errors can occur, and that can itself be a little challenging, I would say. All right, so this is the basic aspects which, as a good programming practice in CUDA, we should have in our programs. I'll not be showing these as part of the codes here, but these are definitely good programming practices which we are expected to follow. All right, so let's come to the cuda-gdb part, where you have not taken care of, let's say, this CUDA get last error, etc., or maybe you have taken care of that, but still you are encountering error somewhere, because we'll not be doing it all the while, right? Every statement we cannot be doing CUDA get last error, although many people suggest that after every kernel execution you just have that, or after every CUDA mem copy you should have that, and so on. So you can add that. There are other ways in which it can be done using cuda-gdb, just by running through the program. And to have the symbol information available in the binary, we need to compile it with these flags. So what are these flags? Any suggestions? Okay, what is minus small g? To enable GDB, okay. Any other suggestions? Okay, so on GCC, we have this -g small flag, which is for incorporating the symbol information into the a.out. We don't need to worry about the variable names, function names, etc. when we generate a.out, right? These are all offsets, these are all different memory locations. We just go ahead with it because variables are used for the programmer, not for execution. But when you are debugging the program, you want that symbol information to be included, which can actually blow up the binary quite a bit. And therefore, this symbol information is kept optionally, that when you add -g flag, -small g, at that time that symbol information is included, which you can use for, let's say, GDB. Similarly, when you are compiling on the GPU using NVCC, you can give -G option, which incorporates the symbol information of the kernels and the device functions, whatever is happening on the GPU. -g, small g is required because there is CPU code also, there is main, there could be host functions. in your program, and therefore to incorporate their symbol information, GCC should be able to incorporate that in the binary. So therefore you require both -g and -G in the command line. Okay, one caveat because of that is that it can disable certain optimizations, not the optimizations that you have coded into. That is, if you have improved memory coalescing or thread divergence or bank conflicts, or you are using shared memory, all of these are optimizations. These are programmer defined optimizations which are not going to get disabled because of this -G. The optimizations that a compiler is automatically doing, let's say it is finding out, okay, there is a 5 into 3 in your program and therefore it is converting it into 50, right, automatically at compile time itself, so that that multiplication doesn't carry over to the runtime. So this small optimization, or there could be very complicated optimizations which it can do. Let's say there is some pointer which I'm passing which is not getting used inside the program at all, so let me not pass that as a pointer at all. I can remove all its uses and so on. So all its definitions, for example, if it's not getting used. So this is an optimization which the compiler can do automatically, which gets disabled because of this debugging information. Why would one do that? Any suggestions? Yeah, so Sheera has mentioned this -G for CPU symbols, -G for GPU symbols. That's correct. So why would a compiler disable these optimizations? Why do we need disable info? Yes, Sheera is asking. I'm also asking the same. Why do we need to disable this optimization? What is the problem if those optimizations are there?
If there is multiplication like 5 into 10, then we will get to know that error is before or after multiplication part, or it is not multiplying correctly. But if compiler directly computes 50, then we will know that it's either initialize is equal to 50 or not.
Sure, sure. Okay, Parth is saying that it's easier to debug. Okay, so let's understand briefly that what a compiler can do. So a compiler can actually remove certain sentences from the program if those are not useful. So if I have x equal to 0 and then y equal to 1 and I'm printing the value of y, x equal to 0 is not required for the output, and therefore it can just remove x equal to 0 statement altogether, and it can arbitrarily move statements up and down depending upon what it feels is the optimization required, as long as you are getting the expected output, right? So that is what we want. We don't care what the compiler is optimizing this code for. But when you are debugging the program, you expect that this statement by statement execution is happening in the same order as the program you have written. Therefore, we need to disable this optimization. Right? All right. So yeah, so we can run it with cuda-gdb. How do you run it? Just invoke cuda-gdb a.out, and that is going to load that a.out into memory, and it's going to keep it ready. It's not going to run it, but it's going to keep it ready. For running it, well, you just say it's going to give you a prompt on which you just say type run, and that is going to run a.out, start executing from main. That is going to start executing all those statements, and it will just execute that. It will also probably give an error. There are some other effects because of running this cuda-gdb, because you are using the GPU, the graphics processor, which might be used by the Windows Manager, right? Windows Manager not only on Windows but also on Linux, and therefore you might have to stop the Windows Manager. Otherwise, there might be your screen might get blanked or something for that matter might happen. But otherwise, it should not be creating any other problems. And because there are large number of threads, it becomes very difficult if you want to debug information. You want to see the symbols for a particular thread and so on. You cannot keep printing all the information all the while. And therefore, cuda-gdb makes sure that it works with something called as a focus, that you are now looking at this particular thread's execution, then you can look at some other thread's execution and so on. So this focus, it allows you to change so that you are just monitoring a particular thread or a thread block and so on. So in this case, let's say this is our program. I just run it. This is the information that gets printed as soon as you run it via the cuda-gdb. And it gives me this particular exception, not in the red code, but this is something which I have added later. And it shows some information that there was a device 0, which means that there is out of the GPUs that I have, these are the GPUs are numbered as device 0, device 1, device 2. So let's say the first device in that is which was used. There are some other things like some thread information, right? Then there is something called as LWP, and they have some IDs. What is LWP? Can we use cuda-gdb with colab? To the extent I know, no. I'm sorry about that, but to the extent I know, it cannot be used. I think it requires access to the hardware. LWP, any suggestions? What could that be? Any guesses? Okay, LWP is lightweight process. Like we said, threads are kind of lighter in weight, right? So that's called as lightweight process. There is a CUDA exception, device illegal address, and then there is a mention of a focus here, right? So there is a focus, which means that I'm talking about kernel 0, that is the first kernel. Grids are numbered 1, 2, 3, so therefore grid 1. Then there is the grid dimensions. This is the first block in the grid, and this is the thread 0, which is having this. So this is invoked with, I think, 2,10. So block 1 is where this issue has occurred. Maybe it tried to execute this statement for block 1's thread 0, and that is where it occurred, and so on. So there is information about the SM on which it was running. Then there is a warp. So warps are numbered, just that this information is not available to the programmer, and lane, which is the thread. Right? So this is where the kernel call happened. So that is the function that was executing. My file name was gdb2.cu, line number 6. And then after this error occurred, what is the next statement at which this probably occurring? Right? So that is, and then it comes back to the cuda-gdb prompt. Right? So using this, I will be able to figure out, okay, there is some issue with respect to this printf or just the statement before that, and so on. There is some information which you can get about at this stage about the different kernels that you might be having. What is the information about that, which SM it is running on, and so on. So for example, there is this star indicates the current focus. So kernel 0, it does not have any parent, which means that there is no nested parallelism or dynamic parallelism, and so on. There is additional information about all of this. There is kernel invocation and what is the parameter which was passed. So using this information, some of that might be unnecessary for you. For example, this mask information you might not be able to figure out what that is. I also don't know what that is, and so on. This is active, which means that the thread is executing. Thread is not masked. If it is would have been if else statement, etc., or we are invoking this with 10 threads, which means that thread number 10 to thread number 31 in the warp are going to be inactive, and so on. So there are other commands like info threads, using which you will be able to get the information about what threads are there. These LWPs are not the GPU threads. These are CPU threads. Some of them might be forking, communicating with the device driver and then invoking the kernel on the GPU, and so on. This particular thread is actually the one which did a CUDA debug detach, right? So this is probably the one which the CUDA debugger invoked for running the a.out, right? So that is the information that you are getting. There are other, so CUDA threads is the one that is going to give information about the CUDA threads, I mean the GPU threads. There is some information here again. For example, what are the starting block ID, thread ID, to ending block ID, thread ID, because we invoked it with 10 blocks, each one containing 10 threads. So sorry, two blocks with 10 threads, so 20, and so on. This is the PC address, which might not be useful for you, but this information might be useful for you about the part. Yeah, so this is again information about different threads and blocks and so on. And I can switch focus. For example, my focus was block 0, thread 0, but I can now change my focus to block 1, thread 0, and that it outputs as I'm switching the focus to this. And now I can talk about, let's say, CUDA kernel block thread, and that shows me that I have changed focus to this particular block, so that I can see if that particular block's thread has created any problem. So sorry about this. Okay, so this part is done. Yeah, so you are allowed to set breakpoints. I'll just take a couple of minutes to finish this part so that it goes into the first in the same. So you can break at a first instruction inside a particular function on CPU, or you can break using a line number inside a file. You can set the break on launch for a particular function, right? So kernel entry breakpoint, for example. And then you can also have conditional breaks based on different variable values and so on, which can be very useful if there is a repetitive thing, and let's say in 1000 iteration the issue is occurring and not occurring for 999. So that can be useful for conditional breakpoints. Similarly, just pressing enter will allow you to step through. Yeah, these other commands which I'll skip, which may not be very useful to you, but at least it can give some information, some insight about overall our how the GPUs access. For example, we said that there are 10 threads per block, and all other threads within the warp are going to be inactive, right? So that is one nice way to figure this out. And all of these threads are executing in SIMD fashion, which means that all of them have encountered this device illegal address. Right? So just as a homework, just think about when you go through this cuda-gdb, just see which commands you can use to figure out what is the error in this particular code. So in our next class, we'll briefly discuss about profiling, but that will be useful to you. And if time permits, then we'll switch to synchronization again. Right? Any quick questions on what we have seen about the cuda-gdb?
Sir, yes, I have a question.
Yeah, because.
So let's assume that the number of threads running are so large that at any point of time, basically there is interleaving of threads. And when we enter into the GDB, let's say our focus is on a thread which is not running right now,
Right.
but the error has occurred in some thread that is running. So then also will it give that error info?
If this thread is not running but was responsible for the invalid thing, then yeah, so then if your current focus is this thread, then the other threads are not running. So you can make sure that only the current thread is running. Current thread meaning current warp will run. So you can step through the current warp, and that can allow you to execute only that warp. So that is possible. So if you want to have that the error has occurred in some other, then you have to let the other warps run. And if those run and your focus is this focus is only for reading purposes, in the sense that the error has occurred and now I'm switching my focus to, okay, what are the variables in this particular thread and so on. So it's possible that the error, even if it occurs if those are executing, the other warps are executing, the error, if it occurs in those warps, then you will be able to see the error. Right? Because I mean the info about a particular thread or the focused warp, this is going to be possible for you only when you are at the prompt. And if you are at the prompt, that means the program is not running. So if the error has occurred, then it will print the error. If the error has not occurred, then you can still check the values, modify the values, and see if there are any issues. Does that seem reasonable?
Yes, sir.
Any other concerns here? All right, so we'll stop here. Please go through this recording again